Alright, this video is going to be an introduction to error surfaces. Um, so we'll just kind of give a brief, just a introduction here. Alright, so let's say we've got a couple cats here and we're putting their weights on this. Alright, so we've got a cat that's about 6.5 pounds, maybe a cat that's about 8.5, a cat that's 9.5. Okay, just so I get these numbers right, let's just make them even, round numbers. Oh, I can't click that. Okay, let's see if I can get it exactly. Oh, there we go. Alright, they all look good. Okay, so again, the problem we're working on is we have 3 cats, and these are their individual weights, 6.5, 8.5, 9.5 pounds. And say we get a new cat, and we want to take a guess at what its weight is. In some way, so your intuition would be maybe somewhere in the middle, somewhere right here, something like that. Or you could maybe, take the average. So, let's just go ahead and do that. So let's do divided by 3. Divided by 3. And then at the top, we'll do the x value of A plus the x value of B, and then plus the x value of C. Okay, so just the average of these weights is 8.16. So that would be, probably my first guess, right? Is if someone asked me what the net weight of an X cat would be, I would do something like this. Okay, but let's treat it like a neural network, right? So maybe, so let's do this. Let's draw ourselves an error surface, right? So let's draw the error surface specifically for point A. Okay, so let's do the x minus the x of A. So what we have here, so this is some x value. So this is a value we're going to use as our prediction, right? So if we use the value 5 as our prediction, right, then this is the x value of A, which is 6.5. So if this is 1.5 of a distance, so that's what this number is, and then we're going to square it, right? So that's how squared error works, right? And of course, all this is saying is, okay, well, if your cat weighs 6.5 pounds, then the error is going to be 0 at 6.5, and it's going to get bigger as a parabola going to the left or right. Okay, so it's probably about what you'd expect. And now let's go ahead and grab this, and let's do the same for point B. Okay, and then let's do the same for point C. Oops, C. Okay, so each of them have their error surface right here, and okay, yep, all of them have their error surface, and let's just go ahead and add them together because that's the total error. So f of x plus g of x plus h of x, right? And now if I hide these, this is our total error surface, right? And so it's just the sum of these things. So you'll notice, at this point, which is the minimum, this height is just the height of these 3 added together, right? So that's all that is. And, so what this is saying is if this is our error surface, this point right here, using this value as our prediction, this is the optimal value because it minimizes the squared error surface. Okay, so let's just go ahead and use GeoGebra to find this extremum here. Boom, D. Okay, well, let's look at D. What do you know? 8.1666. That's exactly the mean that we found. So that's sort of just a fun side note is that when you have a squared error, when you have squared sum of squared errors, the minimum point of it is always going to be at the mean of those values. So that's just a fun side note. But the kind of the moral of the story is, just this is what an error surface feels like, right? So you've got your points, you've got your trainable parameter, which is basically for us, it's just the mean, it's just the value we're going to pick, and we're going to use the mean. But you just find the minimum of that error surface, okay? So the next few videos, of course, we'll get into more interesting things, but we'll kind of leave it there for now.